All right, so we're back with more coding. Where did we leave off last time? Well, we left off at training and we actually had injected conditional sampling in the training loop and unconditional. Now, the problem is it does take a bit of compute, but it's fine. So the one piece that we're missing is if we do this early, it's gonna crash. But let's, just for fun, no, but we don't want to do this, right? We need to plot the samples. And we should also run estimation. So today let's focus on the data pipeline because we loaded training data. We don't really have validation data, right? So let's see, what do we have here? Where did we leave off? Right now we just have a thing called data set, which is really train. This should be train data loader, train data set, and train data. Okay, so it should be train data set, train data loader, get data. Now we also need, of course, a validation data. We can't get the same config data though. We have to change one field in it. If I remember correctly, this data config tag. So we need to get this with data tag. Here it is, config data. So what do we do here? We can change this in. This is obviously tag train val. Data there is the same. Okay, let's just get config data. We'll just make another config here. Val. It's the same directory but with val, and then train is with train, of course, val with val. The problem is I'm kind of hogging the interface here because now I have like 5 configs, which is getting pretty ridiculous. But we can use Pydantic next time, which is pretty nice actually. It's very clean Python. Okay, so now we have config data train and val. Config data train and val. Okay. The model is given by the config data train. That makes sense because the model has to be aware. The train data is given by config data train. The val data is given by config data val. Oh, somebody followed. Thanks for the Twitch follow. Appreciate that. We're just working on diffusion models for inverse problems over here. And we sort of have the full pipeline going. I don't know if you've been watching or not, but it's fine. Thanks for stopping by. Feel free to lurk or ask questions. So I was about to get the val data set. Okay, this is obviously val data and the val data loader, which is obviously the same thing. Shuffle through, config. Now this one will have a fixed, let's just get 4 samples for validation every time. Of course, to be fair, we also need a config val. Yeah, we're not gonna do that. There's way too many configs already. Val data set. So now what we can do is we can actually pull some real data at validation time. Finally, very good. All right, so let's just plot these samples, right? So plot the synthetic data. Actually, you know what would be nice? If the batch size here would be the same 4 actually. Damn it, so maybe I do need a config. Do I really need a batch size here? Config val. Wow. I'm gonna plot 4 random samples. So I'm just gonna plot them for I in range this. So we'll do a subplot. Let's plot them all on the same line, I guess. So one line, this number of columns, I plus 1. And we can just show synthetic samples of I. CPU dot numpy. Well, actually, we can plot the absolute value then. Absolute value dot CPU dot numpy. And that's it. PLT axis off because we don't need axis labels. And that's it. We can do a tight layout. And we can save this. Should we save it in plots? And we're going to call this conditional. And complex to real. This is where we need the actual val samples, and we need the measurements to be actually generated from the. So now we got to replace the init back with val samples. Gotta be careful here. Okay, here we go. Okay, so now we finally need to. Well, let's get the val samples here actually, right? So get a batch of validation samples. Yeah, thanks for stopping by. Thanks for chatting. Val samples. It is a okay, so hang on. So let me get the val samples, which is just next iter val data loader. Why did I have this 0 here? Oh, I see, because I use a tensor data set. Ugh, it's so annoying. Okay, so now we have validation samples and we pass them to the conditional. And finally, we can also measure reconstruction error, which is finally the goal in our paper, right? Because we can say, first we plot, but we can say recon MSE equals, this is just torch linalg dot norm. We can just immediately do this. Recon samples minus val samples. Oh, whoops, not here, sorry. Recon minus val samples. Gotta be careful with the norm here though. Actually, let me do this manually because there is a trickery here. Torch sum. If you do the norm of a matrix, it actually does the singular value norm thing, which sounds really bad. Instead, we want to manually do the mean squared error, so this, or the squared error. So torch square absolute values of the difference on dimensions -1, -2, because these are supposed to be complex. -2. Okay, finally we're done. Movie run pre-commit, run all. And then we can track. We can just print validation step, whatever it is, step, MSE, recon MSE dot CPU dot numpy. Okay, so we're gonna get a nice print and everything. And I can actually launch a training run, uv run -m MIMO.train. There's probably gonna be a few hiccups, maybe not. Okay, all right, so not too many hiccups. Validation works. Let's see what happened here. The save directory is not a path. Oh, it's not a path because I need to make it a path. Okay, path models. Okay, well this sampling, this waiting for sampling is kind of annoying. Let me do this trick I used to do. So if step plus 1. Yeah, and it also solves all the dependencies for you. So for example, you know, if I want to add, let's say I want to add matplotlib to the group Siona, because I don't know what these guys did here. Maybe they want a different version. So then it automatically figures out and it adds it to the dependency group, right? So you can create the dependency group for Linux, one for Windows, and it'll figure out everything, or different versions of packages if you want. You can then add optional dependencies, blah, blah, blah. I'm just gonna remove this because I don't really want Siona. Matplotlib in Siona. Okay, so we do this plus 1, so we don't really plot in the first try. Sampling verbose. Let's make this every 500 steps because I want to train the model a bit. But in any case, we're pretty much done here. So we can do UV lock, PyProject, SRC, sampling, SRC, train, git commit, use validation data. And I think we have the whole pipeline now. Okay, so we can push upstream, conditional sampling. There we go. So now let's launch another training run, which should train for longer now. And I think I swapped groups, and of course I forgot. I should have done UV run with the group torch. This is another thing. So I run -m MIMO train. And that's it. It figures out the dependencies and it runs. There we go. So now it runs with PyTorch. Oh, there's a typo here. Loss function at step, not on at step. Okay, loss function at step 0, blah, blah, blah. Okay, loss is going down, so we're definitely learning the prior. Now it's all a matter of, did we get the step size right enough to not get numerical degeneracy? I doubt it. I really doubt it. Where the heck did I even put the step size? Oh, in sampling, of course. And what did I use for alpha 0? 10 to the minus 3. I think this is not good. Okay, so first of all, my training is not even that smooth. Yeah, from here on now the hard part begins, where we actually I have to reproduce the paper, and this is pretty bad because the training is already unstable. Is my learning rate too large? Not really. It's 3 times 10 to the minus 4. Very curious how the samples look like. Okay, it is going down. Okay, so at least we're pretty clean. Then next we can work on logging, like systematic logging of all these things instead of printing to console. And the better CLI, command line interface. Yeah, but we need to wait for the model to go down now, which is not the easiest part. What batch size am I using? Oh, 16 is way too small. And there is a latency too for sampling, I guess. We have to wait a minute. But I'm very curious how the samples are gonna look like. I suspect they're gonna look like junk. Although there is some structure, yeah, there's a lot of things to fine-tune. The other way we can do it is systematically with some library like that is correct. It is You're right. It's exactly right. For the inverse problem, it is unsupervised because it only learns to denoise. It doesn't learn anything during training about the inverse problem. We're just applying it, which is why those inference parameters are pretty nasty. They have to be tuned by themselves. In a way, that's good because they're decoupled from training, but I remember from my grad school days it is very sensitive and you'll get numerical degeneracy. So how can we make that? Now, what I was going to say is there is this Ray tune library, which you give it an experiment and it... Ah, come on. Okay. I knew I had tensor issues. Ah, because I never moved the samples to GPU. My bad. So val samples to almost there. Model.device. This is how we move them, right? Yes. Actually, this should be model.device, not config. Let's see, where else do we use device? Yeah, we should always use model device to make sure everything stays, except obviously for the model. Okay, what I'm gonna do is I'm gonna skip the unconditional one because it takes, well, actually, wait a second. Oh, you know what? These, oh, here's the samples. I gotta tell you, these are not too bad. This is not Gaussian noise, right? There's some sort of MIMO clusters in here. And actually, let's do this. Why don't we plot the 4 real ones on top? So we sort of know how they look like. Again, validating these is a bit hard. You need a bit of domain expertise, but this is actually pretty, well, it's pretty bad, but there is, I'm seeing some, I think I see some structure here. You can see some patches here. So why don't we do this then? Because this is also interesting. How the heck would you ever debug this? Even for images, right? You would have to just look at them. Now there are metrics for images, like perceptual metrics for whatever neural networks. But for channels, it's even harder because unless you're used to, which I kind of am a bit, that's why I recognize them. But let's do it this way. Let's plot instead. Let's leave the synthetics in and let's plot 2 rows. And on the top row, okay, so here we skip. Let's make this the bottom row. But then on the top row, let's just plot the 4 real samples, which have no relation to the synthetic ones, but we can sort of see how they look like. Okay, so let's make this im show. Aha, this implies I'm gonna need these faster now, okay? So let's get these at the beginning. Okay, so then I can just plot these because I know they have the same shape. Yes. Okay. Now we fixed a few more things. We should be good to go now. Let me delete this. So let's try again, and we're back to the waiting game now. But this is not the worst. If I see structure, then it's only a matter of tuning the alpha parameter, which I remember is the most important one. I can look at my old code to see what it is, but I don't want to spoil it for myself. Yeah, I would like to rediscover this. This seems okay though. This seems pretty conservative. Maybe DR, maybe my decay is too fast too. 0.99 noise level decay. So what do I do if what do I get if I... No, but it should be fine because we did this calculation, right? If I... What is 0.99 to the power of 1,000? Yeah, this is my terminal noise power. So this is basically a noiseless signal at the end of the sampling, which is what you want. So then my noise starts from 10, which overtakes the signal completely, and it decreases exponentially. Well, that's what it should do in the sampling chain. Of course, while still reconstructing, which is all up for debate if it actually works or not. I'm not happy with this training though. The training is really bad. 3 10 to minus 4. It's my batch size. It's too unstable, right? I think I remember this. Yeah, if I make the batch size larger, the training will be more stable and it'll go down. But maybe this is what we want. I would like to systematically experiment with all these. Okay, let's just see the plot at least working. If I get another PyTorch error, I'm going to be upset. Let me just preemptively, let's look here to see what we have. Matmul, this is CUDA int, undersampling, CUDA. What's going to happen is we'll get nans though, so we'll probably won't even see the plot. Noise, how much noise do we add? Very little, right? I think. Yeah, 001 is very small noise because it's squared in power. And then my signal power is 1 because I normalized the data. So then the SNR is like 40 dB or something, which is pretty good. Like it's pretty much pristine, right? So it's only a matter of undersample. Now I can make undersampling 1. Right, which will give me a very easy inverse. Maybe we should start with that then. Maybe let's do that. That's a better idea, right? Because now we get 6464. So we get exactly... Actually, this is a very easy problem now because it's 1 and with low noise. Okay, I got again. Ugh, where? Why? It's gotta be the last thing, I swear. 153. Yeah, the funny thing is I think I omitted some stuff from the, this is... Oh my god, I need to do val samples equals. I don't think I even say the value of alpha. That's the real problem in the paper. And this is why I'm doing this, because I know it's in... What you have to do is you have to look at the original code under the UTCSI lab. There you'll find the real values, but the code is very, very messy and it's really not clear how I even got those values, which always upset me. Okay, I'm gonna skip the unconditional for now, but we can see what it did at... Okay, my plot size is screwed up. The channels... Yeah, okay, they don't... So this is how they're supposed to look, like the top row. Obviously, they're not there yet. Also, my figure shape is out of whack. So let me just do a no fig size for now. No, let's just do how they want it to type. Okay, again. In any case, the pipeline is full now. It's actually full now with inverse problems and everything. So... it's just a matter of finding the exact values in the paper, and I think we're pretty much done. Then we can work on improvements, and we have to clean up the interface. But yeah, if you're watching on YouTube in the video, thanks for watching, and stay tuned for the next episode.